This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. In the last lecture, we discussed the basic Brayton cycle and discussed different ways that we can improve the efficiency or net watt output of this cycle. So basically, there is a few things we can do in terms of improving the cycle. One is to increase the turbine inlet temperature. So on the basic cycle, that's called T3. That essentially refers to the turbine inlet. So this is something people already realized and actually already achieved as much as possible, right? So this already used to the limit. Another one, based on the equation that we derived in terms of the cycle efficiency for the Brayton cycle, we found that if we increasing the pressure ratio at the compressor, just from the equation we can directly tell that the higher efficiency can be obtained. All right, so that's efficiency always goes up with the pressure ratio, but we discussed that we want to pay attention to the net work output. So you don't want to trade off the net work output too much with efficiency, because efficiency will be a diminishing return at some point, right? So that's we'll need to consider the work output. And also we discussed that the compressor and the turbine are not always 100% efficient, so we can increase the compressor efficiency and turbine efficiency to better design this turbo machine to improve higher to reduce the loss in these devices. And we also discussed we can add additional component to the basic cycle to make the process more efficient. So one, we discussed this so-called regeneration. Regeneration, so basically the principle is to utilize the heat coming out of the turbine, because the turbine exhaust of the turbine is still pretty hot. And if you can use those enthalpy there to heat the compressed air, you can save some energy that you added at the compressor. So that's basically to utilize turbine exhaust temperature. Right. So another modification of the basic cycle we can do is a further development on the regeneration. In addition to add a regenerator, we also add two additional components. One is called intercooler between multiple compressors and reheater between multiple turbines. So that's the next thing we're going to discuss. So in terms of why we want to do the intercooling and the reheating, that's related to the work that needs to be done at a compressor we want to minimize work that is done by a compressor and maximize work that is delivered from the turbine. So if you consider you have a reversible process going through a compressor or turbine, if the process is reversible, then the work can be calculated the work for this reversible process can be calculated as V specific volume or mass specific volume dP with a minus sign in front of it. So this is I'm not deriving here, but it's in one of the tutorial problems. So tutorial we are starting on Monday, and there is one on the 5:15 on Monday. It used to be two, but there is one got cancelled. So pay attention to the session you registered. So we are starting on Monday, and you will see one of the problem there. So if you have a reversible process, the work done by a compressor or by a turbine can be described by this equation. So you can see that if we have a compressor, across compressor temperature going up, and the volume always positive, so you have a negative sign saying this is a negative work being done to the system, because this is a work done to the system, not done by the system. If you have a turbine, the pressure will drop, then you will have a positive work. Right? So this minus sign is there. But if you have going through a compressor, if we want to minimize the work that is done by the externally to the gas, you want to keep the volume as small as possible, so that you can minimize the work that done to the system, right? So this volume, when you're going through a compressor, let's say it's ideal process, it's isentropic, which means this volume will goes down after during the compression process, right? But because temperature will go up during the isentropic process, so the volume actually will go. It's not necessarily go up compared to the initial state, but it will, because temperature goes up, the volume will correspondingly become larger compared to no temperature change case. So the intercooler, the purpose of intercooler is to keep the temperature low. So even though going through an isentropic process, the temperature goes up, the volume goes down, you want to keep the temperature always low. So you take away some heat from the system so that this volume will stay low, so you can minimize the work that is done at the compressor to the system. Right? So the point is, because the pressure is the initial and the end, that's something you cannot change much, but if you can keep the volume low, then you can minimize the work, required work down to the gas. All right, so to minimize compressor work, to keep the volume as small as possible, so that you can reduce the compressor work. So this is where the intercooler come in, or intercooling come in. Intercooling is something that you do not using a one compressor. You actually using at least two stage. You divide the compression process into two steps using two compressors, and between the two compressors you're using a heat exchanger to cool the gas. So that's called the intercooler. And similarly, if you have the turbine, during the turbine which you're going through an isentropic expansion process, so there the volume will goes up, right? Because the pressure goes low, pressure goes down. If you follow the isentropic law, the volume will goes up. but at the same time, the temperature will goes up if you follow the isentropic law. And then if you can keep the temperature at the same level or even higher, then the volume will be higher. So in that case, this volume will be larger. You can get more turbine work out of this process. Right, so that's the idea. That is to maximize turbine work and keep the volume as large as possible, so that you can increase the turbine output. So that's called reheating, which means similarly the turbine is two-stage at least, and between the two turbines you have a heater. Again, it's a heat exchanger. You add additional heat to keep the volume up. All right, so that's the idea in terms of increase the overall heat work output from the cycle. Right, you reduce the work requirement at the compressor, and you increase the work output at the turbine. So overall, the cycle will have larger work output. So if we're looking at how the schematic looks like, that will be easier in terms of understanding. So we starting with a compressor. All right. So this is the first compressor. Then going through intercooler. So it's essentially just a heat exchanger to take away some of the this thermal energy of the compressed gas.
Connect the intercooler to the other side of the regenerator.
To the other side of the.
You're taking heat out. Why don't you put that heat back in at the regenerator side?
You could, but that's you got a limit in terms of if this temperature is not hot enough, it does not help. It needs to be hot enough in order to help the compressed gas getting high temperature. But that's a good thought in terms of utilizing the don't waste any energy. Yep. And then this compressor is connected to the second compressor. So C2 there. Then they get to the combustor. All right, then they're going through the turbine side. The first turbine. And again, the turbine is connected to the compressor. And when the gas is partially expanded, it's going through a device called a reheater. And then going to the second turbine. Right. So the idea, again, as said, with the intercooler, you take away some of the heat from the system and keep the volume low to reduce the compressor work. And in this case, you keep the volume up to increase the turbine work. All right. So with this, you can have the net work goes up, right? So with these two combined together, the net work output will be going up. But in terms of thermal efficiency of the process, you actually working against the efficiency of the process. So if you're using intercooler and or reheater, the process, you gain more work output, but you lost efficiency. The thermal efficiency is lower, and the reason for that is if you're looking at the Carnot cycle or the theoretical cycle in terms of efficiency, we learned that this one can be written as the T cold over the T hot. So this is the temperature of the cold reservoir and the temperature of the hot reservoir, right? So by put an intercooler here, so the TH is here, right? TH is the temperature leaving the combustor. That's the hot temperature, and the T cold is the temperature leaving the turbine. By put an intercooler here, you drop the temperature getting into the second compressor, and drop the temperature getting into the combustor eventually. So you reduce the temperature of the hot reservoir. And on the other hand, when you're going through the turbine, two turbines with a reheater, you're increasing the temperature leaving the turbine eventually, right? So in this case, this temperature at the cold reservoir is going up. So these two, if you do any one of these, you will drop the efficiency, but if you do two, then definitely will drop the overall efficiency of the cycle. So that's why when you're using intercooler and or reheater, you always want to using the regenerator to make up the efficiency loss. So that's why I leave some space here so that we can add the regenerator here. Regenerator actually is more efficient in this case because you have a higher temperature coming to here, and you have relatively lower temperature on the other side. So actually, that works pretty efficiently. All right, so that's a system looks like when you're using intercooler, reheater, and regenerator together. So what I want to do next is to draw a TS diagram for this cycle, which is a bit of complicated, but should be pretty straightforward in terms of if you follow the process. All right, first I need to mark the states. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, 10 states. Our TS diagram. The first is the initial state. We go through a isentropic compression process. So 1, 2, 2. And then the intercooler is essentially a heat rejection process. The heat rejection process, basically you have a flow going through a heat exchanger and lose some heat. That's a constant pressure process. We'll have a constant pressure curve there. And in that process, we drop the temperature. Drop the temperature from here. Because the temperature is lower, the entropy will be lower. So if we have a constant pressure line there, we should go this way because the entropy is temperature is lower, entropy is lower. So we go this way to the state 3, right? Then the state 3 goes to another isentropic process to state 4. Then going through the heat exchanger, let's say somewhere there, to pick up some heat from the heat exchanger. So the state 5 there. Then going through the combustor. So that's state 6. All right, then we have the going through the turbine to the 7. Again, the isentropic process. And then the reheater. The reheater is essentially another combustor. Can consider this as just a smaller combustor happening at a different temperature, a different pressure, because pressure now is lower than the combustor pressure. So you're going up there, and then going down. I should have drawn it here. And then go all the way down to state 1. And somewhere here you have the state 10, which means the exhaust, the turbine exhaust gives some of the enthalpy to the compressed air there. All right, so this is how it look like in terms of you have additional 3 components in the system. And on typical cases, you would have the pressure ratio between 1 and 2 versus 3 and 4 being equal. So basically, I didn't draw it very accurately, but basically this 2 state is about level, and this 2 states about level. So that's with that setup, you can minimize the minimize the compressor work and maximize the turbine work. All right. So in this process, if we want to calculate the efficiency, right? So there is a few terms we want to determine first. So in terms of the compressor work, so compressor doing work here and here. So WC1 and WC2. And the turbine also has 2 works, WT2 and WT1. So the total compressor work is WC1 plus WC2 should equals to CP T2 minus T1 plus CP T4 minus T3. Right, so that's the compressor, and the turbine just the other on the other side. You would have the CP T6 minus T7 and the CP T8 minus T9. So each has 2 components, and the Q in. The Q in should equals to this part, because the combustor only starts from state 5 to state 6, right? So the heat is only added in terms of CP T6 minus T5. So that's that's the heat added as a combustor. We also have the heat added at the reheater, right? So that's another component, the heat addition. So we have the CP T8 minus T7. Then in terms of efficiency, you can find that is WT minus WC over Q in. So that should be pretty straightforward. As long as you understand how the process goes, and then just in terms of math, that's very straightforward. You need to understand the process. Math is not really challenging here. And also, what I want to you want to be clear is there is energy balance at the regenerator. So you would have the temperature difference between the Cp T9 minus T10. The temperature difference between these two states should equals to Cp of what temperature difference? 5 to 4. Yeah. T5 minus T4. So that's the energy balance at the regenerator. So again, I assume this is an ideal cycle. There is no heat loss in the system. All right. Any questions? So this is the end of the Brayton cycle. So we'll move to another gas turbine cycle. If you have any questions or not. Okay, should be pretty straightforward. So the cycle analysis part is I consider in the thermodynamic study that's probably the most straightforward part, because you don't need, in terms of math, that's cannot be simpler in terms of at the college level, and but you need to understand the process, understand from one step to the other what happened, and what energy balance you want to apply to the system. All right, so if no questions, we just start the second part of this chapter. So this part we call as a turbojet cycle analysis, and that's based on an ideal cycle called a turbojet cycle. And this is an important application of the gas turbines, although in reality the actual turbines do not run on a pure turbojet. It's always something called more like a turbo fan. So we are going to discuss it later on. But the turbojet is an ideal case. And you can consider that's actually an extreme case relative to the Brayton cycle, because this cycle has all its output as the thrust. So it output 0 shaft work. All the enthalpy in the process is being used to produce the thrust in order for the aircraft propulsion. In reality, the turbo fan, which is you can consider that's somewhere between the turbojet and the Brayton cycle, produce partially shaft work and partially thrust. Right? So the useful output here. So thrust is a force. So if you want to write or to calculate the thrust basically is an unbalanced force applied to the aircraft to push it to go, right? So the force can be calculated as the m dot delta v. So the m dot refers to the amount of air that you can accelerate. Let's be more clear. So it's basically the amount of air passing through this engine or passing through this turbojet, and the velocity is the velocity change passing through this device. So the velocity of the outlet minus the velocity of the inlet. So depending on how much air you can accelerate, and depending on how much velocity increase you can produce, it will generate a larger thrust. And in terms of the energy form, thrust corresponding to what type of energy form? So in terms of a high moving jet, which is produced from a combustion process. So we consider this process is converting the thermal energy to what form of energy? Yep. So that's the, I didn't ask the question in the right way in the first place. So if I ask correctly, you know the answer. So in terms of energy form, that's the kinetic energy, delta Ke, right? And delta Ke can be written as m delta v square divided by 2.
Move the paper.
Okay. All right. So in terms of the cycle schematic, that's pretty similar to the Brayton cycle. So if we're looking at a more complete version, we're starting with something called diffuser. And this diffuser then connected to a compressor. Right, the compressor then going in a combustor. And the combustor to drive a turbine. And then the turbine, the function of turbine is basically to drive the compressor, essentially. This turbine does not output the useful work. So the unused thermal energy from this process then going through a nozzle to produce the thrust. All right, so this basic layout is similar to the Brayton cycle, except that we have two components, which is a diffuser and the nozzle. It not always have a diffuser, but the nozzle is always there. So let's look at some picture in terms of how this thing look like. So this is one of the very big engine. It's a Rolls-Royce engine installed on the Airbus A380. So it's the largest passenger aircraft built to date. But if you heard the news, unfortunately, they will stop building it in 2020 or 2022. But anyway, there is quite a few still in service today. So this is a huge engine, and if you're looking at the major component here, so you have a fan at the front, and then there is a series of like rotor, stator as the compressor, which is a lot of stuff going on here, and then you're going through. There is a multiple stage going from low pressure to high pressure. Then you have the combustor part. Combustor is where this red section is, which is very small compared to the overall volume of the engine. And then you're going in the turbine section. Turbine is also multiple from high pressure to low pressure. And you can see actually when going through the turbine, the temperature is going down, so the color is going from red to yellow, and then to the color that you can now see. So if we look the cross section inside, so you have a fan at the front, and this fan, the function of the fan is more like a low pressure compressor. Then you're going through this intermediate pressure compressor at this section, and then go to the high pressure compressor side. Then you have the combustor, which is a small volume over here. Then the multi-stage of turbine. Then you have the nozzle at the end to produce the thrust. So most of the compressor used in gas turbine, probably it's difficult to find a case which is not using this type of compressor. This is called the axial compressor. So we are going to see a YouTube video on this, so you can have a closer look in terms of how this type of compressor look like. Right.
The problem on the computer in the right,
Oh.
right side.
Okay, yeah, thanks. Hopefully it's not too loud.
Compressor. Everybody knows that the intake of a jet engine is where the air goes in, but what's behind it? The spinning compressor blades. Okay, all the diagrams, they show jet engines as a bunch of fans spinning around in quite a few spaces. Pretty simple, one big piece moving, a few things not moving. Seems pretty simple. There's the intake of a turbojet, and we're going to take a closer look at the compressor and the stators to see just what kind of spaces exist in there. Okay, let's take a look at another compressor rotor. Okay, tucked in amongst all the other stuff in the shop, this is the compressor rotor of an LM1500 J79. This is the back end of it. The intake end is right here, facing the floor. That's what the air first encounters, these blades. You can see the spaces between the rows, and those match up with the stators in the case. Where does that rotor fit? And what does it work with? Well, we have one set of cases right here. Let's take a look. This is the matching compressor casing from an LM1500. And inside all these stators is where the wheels of the compressor turn. You can see there's not any extra space for things like birds and gum wrappers to fly through. So over there, there's the compressor rotor, and it fits right in here. And it's very tight. There is no room for anything else except for the compressor rotor inside these cases. The diagrams that we see don't show every stage of stator. There's a stage of stators behind every stage of the compressor rotor. Each of the stages of the compressor rotor matches up with one of these slots, except for this one. Now, we've covered this in a previous video, a couple of years ago actually. These are called the outlet guide vanes. They're a form of compressor stator, but because they're the last thing that the air sees before leaving the compressor, they're called outlet guide vanes. You could call these stator guide vanes, but they're usually called stator vanes. Outlet guide vanes. This is a two-piece design. There's no rotor stage in there. The 17th stage of the rotor is here, and the air contacts this stage, or sub-stage, I guess, and then this one can be directed straight back into the diffuser, which we covered recently. Look the way it looks with a case half off. Pop the hood, so to speak. Look at that. Look at all the stators lined up with the... Now compressors, axial compressors anyway, they're all different. They come in all different shapes and sizes, but they all are kind of the same. Let's take a look at a little tiny one from a 1400 horsepower engine we had in here last week. Look at this little guy. Well, there is a medium-sized gas turbine engine compressor. Merci, what engine is that out of?
Solar Saturn.
Solar Saturn. How much horsepower?
This one, 1400.
1400 horsepower.
Just pause here. 1400 horsepower, which is about, if you time 0.73, it's about 10,000 kilowatt, right? And we said for a car engine is about a typical car engine, 4-cylinder is about 100 kilowatt. So that size of a compressor, you can say is like of a comparable size as that person's hand can produce 10 times of the a car engine. But certainly that's only for the compressor side. You also have the combustor and turbine attached to it. But just saying that for a small size of gas turbine, it can produce a lot of power. As said, the gas turbine has the highest power density compared to the other type of engines. And also you can see that the the rotor and the stator, they have to be machined with high precision. So they have to made at the right position, and also they have to made in the right way, which later you will see. It cannot be totally fixed to the rod. It has to have some free play in order for the things to run properly. So the whole process has to have a high precision machining involved, and that makes this type of engine more expensive. All right, let's continue.
Cool. Can I have it?
Yes, yours.
Now let's take a look at these. They're a bit loose. This is normal. This is the way they should be. So there's no real resonance. They don't ring like a tuning fork like some of the other rotor blades in other videos. Those, actually we'll take a look at those right now. Here we are outside with our cutaway. This is the exact same thing we were just looking at. This is an LM1500 J79 rotor, and what's different about these blades is they're all rusted solid into their wheel. They're corroded and full of dirt right down there in their mounting, so that they're solid. This is a very dangerous situation if this would be a running engine, because they'd probably start to ring and vibrate and crack. This is our cutaway model. And that's the sound of dirt trapped down in there. You can see there's the matching of the compressor rotor and the stators. Oh look, we're missing some stators right there. Anyway, that's how closely it matches up. And you can see which parts move and which parts don't move. Those are the passages through which the air must pass to be compressed. Okay, so it should be quite obvious that anything that goes in there has no chance of surviving. Okay, we're out here in the graveyard of turbine engines with a turbine-powered helicopter in the distance to look at how does a compressor blade wear out. There's two examples on this one right here. This is a stage 1 blade from an LM1500, and let's see if we can get in there real close. Okay, we're moving in here to the blade root, right along there. This is the surface that bears the centrifugal load of the spinning compressor rotor, and I hope you can see there's some wear. This blade, on inspection from removal of an engine, was decided there's too much wear there, so we junked it. There's another very good example of what happens. This can't be repaired. What can be repaired up to a limit. This is the leading edge of the compressor rotor blade. You see that rough texture with all the little pits and holes and moon-like surface? You see that leading edge? All the pock marks from tiny particles of solid debris, sand or dust, smashing into that at very high speed. This is a solid stainless steel blade, so you can get an idea of the energy and the speed of this thing. 7,200, 7,400 RPM. To repair this, all this would have to be filed away and then repolished to a nice smooth leading edge of the airflow. This one could be fixed, but because of the root wear, we junked it. This is why intake air filtration is so important for an industrial turbine engine. They run for much longer periods of time between maintenance than an aircraft engine. Once again, thanks for watching.
All right. All right. That's a pretty good introduction in terms of how aircraft compressor works. So in terms of the why it cannot be brighter? So in terms of the cycle analysis, if we are having this, we call the turbojet cycle, there is a two major difference that you want to pay attention compared to the Brayton cycle. One is because we have two new components here, and these two new components, the process across them is somewhat different compared to the one we seen before. So here, the kinetic energy change across the diffuser, and particularly across the nozzle, are not zero. So you have to consider that the kinetic energy term on one side of this process, right? But everywhere else, you still can consider that the kinetic energy change is zero elsewhere in the cycle, right? Another thing is in this pure turbojet cycle, we consider that the turbine does not output useful work. As said, the function of the turbine is just to drive the compressor. So the work at the turbine is equals to the work of the compressor. So that's for this pure turbojet cycle. All right, so based on this, we can, I guess first we need to understand how the energy got converted at these two new devices. Then we can draw a TS diagram and calculate, do our typical calculations. The process across a nozzle is pretty straightforward. So the energy diffuser is essentially the reverse process of a nozzle. All right. So cross the nozzle. If we call this 1, 2, 3, 4, 5, and 6. So if we apply the energy balance, which is the first law, to the process, we have the Q minus work equals to delta or H6 minus H5. So that's changing enthalpy. And we said this process, you cannot ignore the change in terms of the kinetic energy. So let's say the 2V6 minus 2V5 squared, V6 squared divided by 2 minus V5 squared divided by 2. That's the change in kinetic energy. Right? So that follows the first law. And this process, we said the process going through a nozzle is what type of ideal process? nozzle and diffuser is one type. The process going through it is an ideal process, and that process is isentropic. Isentropic, and in our discussion here is adiabatic. Yeah. So again, nozzle and the diffuser, they are isentropic device, right? Because isentropic, by definition here, it's adiabatic. So that one goes to 0, and the nozzle does not do any useful work. It's not a turbine, right? It has no useful output. So this one also goes to 0. So you have these two terms equals to 0, right? So here we consider that in general, this term is very small compared to the rest of the terms. So the velocity at the nozzle inlet compared to the velocity at the nozzle outlet is very small, particularly consider this energy term. Then you can find the H5 equals to H6 plus the kinetic energy term at the nozzle exit. So across the nozzle, you have the enthalpy being converted to kinetic energy and some leftover enthalpy in the process. Right, so that's something you want to be aware of. Nozzle is a device to convert enthalpy to kinetic energy. And as a diffuser, that's a similar thing, just reverse process. At the diffuser, if we have state 1 to 2, we have the kinetic energy coming in and the enthalpy coming in, then equals to the enthalpy of the state 2. Again, here the velocity is not 0. I should say the velocity, certainly the velocity cannot be 0, otherwise it cannot passing through this device as a flowing system, right? But the kinetic energy term is very small, so I just ignore the kinetic energy term there. All right, so with these two, then we can draw the TS diagram. So in terms of TS diagram, starting from the entrance, which is state 1, going through the diffuser first is an isentropic process, even though it's a kinetic energy being converted to enthalpy here. So we have a vertical line. That process is isentropic to state 2, and the state 2 going in the compressor is again that's an isentropic process. So we keep going on this straight line to state 3, then going in the combustor state 4, then going down, passing through the turbine to state 5, and then enter the nozzle. Again, nozzle is an isentropic process, so we just keep going to the state 6, then connected to the state 1. So one thing you want to be aware of is the temperature difference between 3 and 2 should equals to temperature difference of what two states?
Why in the point 1 to point 2 they are like increasing temperature? Point 1 to point 2.
Okay. Yeah. So let me answer your question, then you guys answer my question. All right. Sorry. So the diffuser is the process going is a process that converts the kinetic energy to enthalpy, which we do here. So you're going through 1 to 2 is a diffuser, right? You have the kinetic energy coming in. You consider that the aircraft is flying at a pretty high speed, and then you have the air coming at a certain velocity, and that velocity when going through the diffuser being used to raise the enthalpy of the gas. The enthalpy, high enthalpy means high temperature. So that's why I'm going up here.
But point 2